Okay, let's do a review. So first, we know that we need to be able to add two complex numbers. So if we add a couple of complex numbers, -4 plus 4i minus -6 plus 9i. We distribute that stuff and we get 6 minus 9i. But then if I add the real parts, I get 2. If I add the imaginary parts, I get -5. So we're really just treating these like binomials. So when I multiply these complex numbers, again, you can use the distributive law twice in FOIL, or you can recognize that it is in the form of a minus bi times a plus bi. It's just a difference of two perfect squares. So it's the first one squared minus the second one squared. But 2i squared is -4. Negative negative is positive, so we get 20. Here, if we have 2 minus 3i over 4 plus 3i, we look at the bottom and we multiply by the conjugate. The reason is we wish it was of the form a plus bi, because we know that one complex number divided by another should turn out to be a complex number, a plus bi. But the only way to do that is to get rid of this I in the denominator. So we take the same two terms as here, but we just change this middle sign from a plus to a minus. We got to do the same thing on top and bottom. So on the bottom, it's the difference of two perfect squares, like it will always be. And so that ends up giving us 25 on the bottom. And then when you multiply out the top, we just distribute and get these two terms. Then we distribute and get these two terms. But then 9i squared is the same as a positive 9 times a -1. So it's -9. But then that -9 and 8 gives us -1. And these two give us -18i. So it ends up being this over 25. But then we break it up. If you have two things added over a number, you can break it up into this one over 25 and this one over 25 times I. Here, we're wanting to make it a complex number, so -20, if you take its square root, well, 20 is just 4 times 5, and -20 is just -1 times 4 times 5. We can take the square root of each, and the square root of 4 is 2. The square root of -1 is I, and so we get 2i squared roots of 5 is what this is equal to. We make the replacement, and then if you have two things added over a common denominator, you can break it up to have them each over that common denominator. When we simplify, we get 2 plus 5i. Let's see, so there was that. Then if we look at number 5, we're going to have I to the 15th, but because that's an odd number, I'm going to pull out one I. And the reason I do that, because I to an even, I can rewrite as I squared to some power. So I squared is just -1.
Excuse the quick interruption. Teachers, at this time, please allow students competing in the Math Madness to leave class now. Students, bring your Chromebook and go directly to room 212. Thank you.
I squared is just -1. If you raise it to the 7th, you get -1 times I is -I. Here, we just distribute, and on top we get this. But then -12i squared is the same thing as a positive 12, because a negative times a -1 is a positive, and we've got 12. So 12 and 2 give us 14, and this gives us 2i. So now we have a new problem to solve, and we can divide those complex numbers by multiplying by the conjugate of the bottom. When we do, on top, we just, again, distribute twice, use FOIL. -4i squared is the same as negative times a negative is positive 4. So 4 and 14 give us 18, and these together give us -26i. The bottom is 1 squared, which is 1, minus 2i squared, which is -4i. That ends up giving us 1 plus 4, which is 5, and then we break it apart. because it needs to be a complex number. Then we solve some equations. This set equal to 0, we just move over the 36 and take the square root of both sides. Do not forget your plus or minus. Square root of negative 36 is 6i. For number 8, it doesn't look like a quadratic, so I distribute to change the form, and then I get everything equal to 0 because that's how we solve things by hand, is we want them equal to 0. So I can't factor, so I write down what my a, b, and c are, and I write down the quadratic formula before I use it. Well, then plugging in, you end up getting 1 plus or minus the square root of 11. Okay, for 9, again, it's the same sort of deal. We're just using the quadratic formula because we could not factor. Also, make sure at the end you break it apart into 2 terms. On 10, I want to know where does this thing, if that's my height of my rock that I'm throwing up in the air, well, one thing you know, when you plug in 0, you get 0 squared and 0 here, so all this goes away when you plug in 0, and you get a height of 8 is where we start. So, to get to the maximum, it should be clear that we plug in h is equal to negative b over 2a, will give us the x-coordinate of the vertex, which is where the maximum occurs. So we get approximately 2.45, so it takes approximately 2.5 seconds, 4 or 5 seconds, to reach the maximum. Now, if we double that, we are not going to get where it hits the ground. We're going to get right about here, where it's at 8 again. To find out where it's equal to 0, I would have to take the whole thing and set it equal to 0. To find out what its maximum height is, I would have to take this value and plug it back in the original to find the height at that h value. If they ask me to graph this thing, I'm going to factor it first like so. And now that it's factored, I know that the x-intercepts are where y equals 0, so I write that down. And so if 3 things multiply together to get 0, either x was 0, 2x minus 3 squared was 0, or x plus 4 squared was 0. But the only way a squared can be equal to 0 is if this is equal to 0, so we get 3 halves, or this is equal to negative 4. Right? So there's our 3 zeros. So then I write down very clearly my zeros, multiplicity, and local behavior. For the 0 of 0, its related factor is raised to the first, so its multiplicity is 1. For 3 halves, that 0, the associated factor of 2x minus 3 is raised to the second, so that 2 is its multiplicity. For the 0 of negative 4, the factor associated with it is x plus 4. Since it's raised to the second, its multiplicity is 2. So anywhere where your multiplicity is 1, you cross locally. 2, you touch. Then I write down y-intercept is where x equals 0, so I can really slow down and be intentional. So you plug in 0 and you end up getting 0. And then the end behavior, I just want to multiply this thing out. But instead of multiplying the whole thing out, I realize I'm going to have an x for my first term times a 2x that's going to get squared times an x that's going to get squared. That's going to give me my first term, and then there's going to be a bunch of other stuff. But that leading term is what determines the end behavior. So I write out my leading term, and I see that it's going to have an odd degree and a positive leading coefficient. So odd positive means down up, and you would write it like this. So putting that all together, you have a graph that has these zeros, the correct local behavior, and the correct end behavior. Similarly for 12, same sort of deal. I factor. I write down that the x-intercept is where y equals 0. I find my 2 zeros. I say for x equals 0, the associated factor is raised to the second, so its multiplicity is 2. For a 0 of negative 1, the associated factor of x plus 1 is raised to the second, so the multiplicity of that 0 is 2. So it looks like I touch at both of those zeros. The y-intercept is where x equals 0, so I plug in x equals 0, and again, just turns out I get 0. It doesn't always have to be that way. And then the end behavior, if I were to multiply this out and get a whole bunch of stuff, I think the first term is going to be this thing multiplied by an x squared. And then I may have other stuff. That leading term is going to give me the end behavior, and so that leading term is going to be 3x to the fourth. Since it's even and positive, I know my end behavior is up, up, which is written like this. Putting it all together, you would have a graph that looks like this. 13 is exactly the same, so I'm not going to go over that. 14 looks like it's going to be exactly the same, so I won't go over that. 15, this is a case where if you are taking x cubed minus 126 and dividing it by x minus 5, the key fact is that you need placeholders. Without these two placeholders, no x's and no x squareds, you will screw this up. So x squared, I'm trying to think to myself, what do I have to multiply x by to get x cubed so that when I subtract, they cancel out? Well, x squared times an x gives me x cubed. And then x squared times a negative 5 gives me negative 5x squared. And I subtract, 0 minus a negative is the same as plus a positive. So I get 5x squared. Bring down the no x's. So then I say, what do I multiply times x to give me 5x squared? So when I subtract, they cancel out. And the answer is 5x. But then 5x times negative 5 gives me negative 25x. So 0 minus a negative 25 is just a positive 25x. And then bring down this other term. Because this has two terms, it wants to attack two terms. Well, then 25 times x gives me 25x. So they're going to cancel out in a minute. But then 25 times negative 5 is negative 125. So this minus a negative is the same as plus a positive, so we get a remainder of negative 1. And then please show this. So what we've just shown is that this divided by this is equal to that polynomial with my remainder of negative 1 divided into that many pieces. 16, if I want to find all the zeros of this, I'm going to find my possible rational zeros by looking at the factors of the last term divided by all the possible factors of the first term. And not really term, coefficient, excuse me. So the last term, these are the numbers that divide evenly into it. Last coefficient. And then the last first coefficient of 1 is the only thing that divides evenly into it. So each one of these might be a 0 using this top and this bottom. So I'm going to try 1, and when you plug in 1, yes, you get out 0. So here's the key fact. Since x equals 1 is a 0, x minus 1 is a factor. Super, super important. So that means I can take my whole thing and divide by x minus 1. When you carefully do that, you get this chunk of stuff. So here's 1 0 that I pulled out. All the other zeros must live in here. So I can rewrite my polynomial as x minus 1 times all this stuff. And so now I have to find the zeros in here. Well, the way to do that is to factor, and since it has 4 terms, I'm going to come over here and factor by grouping. So I look at the first chunk and say what's common to these two. I get x squared, and x plus 3 is left behind. So then from experience, I know in these two, I better be able to pull out an x plus 3 as well. That means I must factor out a 25. So now I view it as having 2 terms, and what's common to both of those but an x plus 3. So when you pull it out to the front, you're left with x squared plus 25. So this is simply equal to this. So you can replace this with what it's equal to here. And so now I have 3 things that multiply together to get 0. So either x is equal to 1, negative 3, or if this is equal to 0, what you end up getting is negative plus or minus 5i. Right? So there's your 4 zeros. And we know for degree 4, we should get 4 zeros. All right. And then the last little bit, A polynomial of degree 311 should have 311 zeros. The max number of turning points is going to be n minus 1 or 310. Two ways you can fail to see a zero on a graph is either the multiplicity is greater than 1 of that zero, or some of the zeros are complex. Lastly, if you have a degree 10, the number of zeros is 10. And the max number of turning points is going to be n minus 1 or 9. Cool. Awesome. Thanks. Stop. Stop. Stop.